Okay, welcome back. So we'll get started from where we left yesterday. We have been talking about, in the previous module, we have been talking about the like a QA/QC, the quality assurance, quality control, the data quality of whenever we try to do data collection. And the focus of discussion has been on waste management, but as I said, it is relevant for other aspect of environmental engineering as well, or in general, even in chemistry or other wherever you use some analytical technique. So yesterday, if you remember, so in the last module, if you remember, we were looking at the QA/QC, and then the next like blank, spikes, replicates. So one of the other important stuff here is to look at the method detection limit. So what is method detection limit? We'll talk about. We'll kind of start talking about that, and I'll do a math to tell you how it is calculated. And that's another big thing whenever you look at any environmental report where the data has been collected, it has been analyzed, and it has been put in form of a table. We see that people reporting many times people even reporting 0. That's actually wrong. You cannot report 0 because we cannot measure 0. So since we cannot measure 0, we cannot report 0 because any machine that you have, how sophisticated it may be, it can measure up to a certain concentration. Below that concentration, the number that you are getting is not correct. It is the machine will give you a number. That's where you as a master student, PhD student, or a researcher, or a faculty member, or whoever is or a technician, whenever you are using an analytical machine, it's many times I get the answer from my students saying that this is what I got from the machine. So it's like a things written in stone. That's not correct, because the machine will give you a number, but you have to make sense out of that number. So you cannot report anything as 0 because you cannot measure 0. So what the minimum concentration that you can report, and that's the minimum concentration, is known as the method detection limit. So for example, if you're using a spectrophotometer and to analyze a certain parameter, so a spectrophotometer can measure up to say 1 ppm or 0.5 ppm or 0.1 ppm or say 10 ppb. So there is a limit to which it can measure. Below that, the machine does not have the capability to identify that concentration because it's too low for that machine. So that concentration, again, I'm just trying to explain in different way. So that concentration we'll call method detection limit. So if you look at this particular slide, this is a regulatory definition. That's why it's a big text. Don't whatever I've been trying to explain you in last a minute or two is what has been given over here. It has been directly copied from the text from one of the like a regulatory document. So that's why it's the minimum concentration. So if you look at here, it is what it is telling you. Whatever I was trying to explain to you, it's the minimum concentration. It's the minimum that of a substance, or we can call it an analyte, that can be measured and reported with 99% confidence. So if again your statistics, if you remember from your statistics class, if you have not taken one, I encourage you to take one, because whenever you do the data collection and try to do the data analysis, statistics plays a big role. You should have a fairly good understanding of the basic statistics, all those t-test, g-test, ANOVA, chi-square, and your regression analysis, looking at the confidence limit, confidence interval. So those are very basic in terms of the statistics, and then you should be aware of that. We cannot cover that material in this class, but those materials are useful. So if you really want to do well in this course, I would encourage you to go and read about it. If you have trouble finding source for that, send us a question on discussion board. We'll be happy to provide you link to some good resource on statistics, especially on environmental statistics. But it's your responsibility to learn that. We're not going to cover that in this particular course, and most of you must have taken a statistics course by this time. So it's a minimum concentration of any substance that can be measured and reported with 99% confidence. So it's we use 99%, 95%, 90%. So with the 99% confidence, and what is that? That's the analyte concentration is greater than 0 and is determined from the analysis of a sample in a given matrix containing that analyte. So I'll try to explain that in one by one. Analyte means the parameter that we are trying to measure, whether it's arsenic, lead, cadmium, whatever you are looking for, or any organic chemical that you are looking for. So that's the analyte that you are trying to measure. The concentration, of course, is the amount that is present. Concentration, usually we express them as mass per volume or mass per mass. So mass per volume will be like milligrams per liter, mass per mass will be milligrams per kilogram. So that's the analyte concentration, and the value is greater than 0. That is, we can say with a 99% confidence that the value is greater than 0, and we determine that number in a given matrix. Now, what is the meaning of given matrix? Yes, in the previous module also I used a term matrix spike. So given matrix means what kind of sample you have. Do you have a clear water sample? Do you have a surface water sample, or a wastewater sample, or a landfill leachate sample, or it's a sandy soil, or a clay soil, or a organic soil? So depending on the type of matrix, those are our matrix, like where our analyte is present. So in that particular matrix. So once because depending on the type of matrix, your analytical capability of the machine also keeps on changing. So what I'll try to just to illustrate, like just to elaborate on that. Say if you're using DI water or a nano pure water, DI water, nano pure water, other than the chemical of interest that you have, there might be some other chemicals present there, but overall it will not be of a nasty kind of material. It's not a nasty material. There is not a lot of other things in there. It's a clean water, so its analysis becomes a little bit easier. So but when we go to landfill leachate or a wastewater, industrial wastewater, there are a lot of things there. There is a lot of organic matter present. There could be sulfide. So there will be a lot of interferences of all the different parameters that is present in that matrix or in that media. So their analytical capability may not be the same as what it was for the DI water. So that's why the matrix is very important. That's the reason we use the matrix spike that I explained in the previous video. So to know whether in that particular matrix we are getting the good response. So similarly here, when you are trying to look at the detection limit, your detection limit may change depending on the type of matrix that you are using. So it's very, very important to know because depending on the different types of matrix, the complexity of the problem changes, because there are a lot of different parameters, there are a lot of different things would be present, and they will try to interfere. So there is called interference. You will have an interference problem. So those they may be competing for same kind of reaction. So there is a lot of things can happen, which it's difficult to explain in this particular course. So this is that's basically a analytical analysis course, and there might be some courses like that either on NPTEL platform, or these days you can even have EDX and other platforms there too. So you can look at that. There are some good books on that as well. But for a normal understanding, you should try to understand that based on the matrix, our analytical capability changes for the same machine. So that's why when we try to go for this detection limit, we have to know what matrix for which it was determined. So again, what is the detection limit? Detection limit is the minimum concentration which can be reported using a particular analytical instrument with 99% confidence interval that the number is greater than 0, and the number is, so like we are 99% confidence that the number is correct. So that's now how we get it. I'll not go in very much basics of that, but just to kind of show you like how what is the method it is being used to and to get this method detection limit. So in terms of the method detection limit, what we do is we use this formula, which is MDL, which is method detection limit. It's your T from your T table. Let's go back here. So your T is your T table, and then S is the standard deviation. Now what is this T? Well, how we got the T, how we got the S, we'll talk about that in a minute. Where T is your one-sided critical T value at 99% level, N is the number of sample, S is the standard deviation. So what we do, we multiply the standard deviation by one-sided critical T numbers. Different T value should be applied based on the number of sample. EPA recommends that minimum, or any regulatory agency requires you to have minimum at least 7 samples. So what do we mean by this minimum 7 samples? I will explain it in the next slide using an example, so that will make you clear what we are trying to say here. Say this is an example. So you want to analyze, you were planning to analyze for one particular parameter. Let's, for our discussion's sake, let's take this data is for lead. So here we had a sample. We did we did different replicates of the same sample. So we had 8 replicates. It is the same sample. So basically it's the same sample, and we have taken out and did 8 of that. 1, 2, 3, 4, 5, 6, 7, 8. 8 of the same sample we have done. So they are like 8 replicates. So 8 times it was analyzed. Let's clean this up. So 8 times it was analyzed, and these are the numbers we got. So the numbers are like the 12.11, 12.02. The minimum one we have is 12.02, and the maximum we got is 12.57. So and then it varies between 12.02 to 12.57. So there is not a lot of variability. So if you have this kind of variability, which is almost like plus minus even less than 10%, so that's really a very good analysis. So your instruments are working really well, and you are a good your lab practice is good. Like your hands on the lab activity is pretty good, because you don't see that much of variability. So this is a good data set, and these are all this I will show you several data sets in this set of slides in this video, and they are all made up just for illustrative purpose. They are not real data, just to explain things here. So but you take an analyte. Say if you want to analyze say lead on ICP, or you want to analyze arsenic on ICP, or arsenic on graphite furnace, GFAA, or you are doing arsenic on flame. There are different things. There are different instruments we can use. You can do certain things on GC. So for any analysis that you are doing, you will take a sample and you will do 8 replicates of that. Minimum is required is 7. So you do 8 replicates, and we got these numbers. So now what we do with these numbers? So we, after these 8 replicates that we got, what we'll do is we'll use that equation that was we were looking at in the previous slide, where now the n is equal to 8. Our number of sample n was 8. We can calculate the standard deviation. A standard deviation for this sample, if you do, I encourage you to check out these numbers. So don't just trust me. I may also make some mistakes. So you check those numbers. So your data has been given in the previous slide. So and you will have the PDF of this whole lecture material with you as a reading material too. And so a standard deviation is 0.19 of the data set that we just looked at in the previous table, which was this table. So if you look at this table, the data, the standard deviation is 0.19. And if you go to T table from any statistics textbook, why it is 7? Because remember that the degree of freedom is n minus 1, n is 8, so n minus 1 is 7. So that's why we have this 7. And excuse me. So this is that's why we have this 7. And then we said the alpha at 99% confidence. So that's why alpha is 0.99. So if you go and look at a T table from any statistics book, the value is 3. So what is our, from that, if you remember the formula that we used in with the formula that I showed you in the previous, the T n minus 1 alpha. So this value is we got it from the T table times the standard deviation. So if you come back here, so this T value is 3. We got 3 from here. So sorry. So with T value is 3. So we got it there. Standard deviation is 0.9. That's what we got it here. Multiplied that, and we got the value of 0.57. So that's the MDL for this particular analyte in this particular matrix is 0.57 milligrams per liter. So what does that really mean? It means that it is 0.57 milligram per liter would be the minimum concentration you can trust with 99% confidence level. So what is to elaborate that? So if you do this analysis for an unknown sample, say for our discussion's sake, we said, okay, this is for the lead. We are analyzing for lead from some water sample or soil sample, and we got these concentration. So if it's for lead, and for that particular water sample, or it could be e-waste leachate, whatever. So it's when we do an unknown sample, the concentration, if it's above 0.57, if the number is above 0.57, so if it's greater than 0.57, we can rely on that concentration. If it's something less than 0.57, we cannot say for sure that the concentration is correct, because the machine cannot measure something with 99 confidence level of any concentration less than 0.57. How we know that? Because we did that procedure as prescribed by like based on our statistics friends. Though there is actually a lot of books out there on environmental statistics, that US EPA and several regulatory agencies, if you go on Google and try to look for environmental statistics handbook, you will find several of those handbooks which gives this how to do this. And to get into that background, that will be like a little bit of a lot of statistics involved, so we'll refrain from doing that. If you are interested, or you are more than welcome to read about it and ask questions on that. But it's so anything greater than 0.57, we are sure, we are with 99% confident that the number is correct. Anything less than 0.57, we are not confident. So when you do this analysis of an unknown sample, you may get a value of say 0.4 or 0.3 milligram per liter, but that number doesn't make any, although the machine will give you a number, but as a researcher you have to decide and you need to say that no, this is below detection, so I cannot trust this number. So its number cannot be, it may not be true because it's below the detection limit. It cannot comprehend that number. The machine does not have the capability to comprehend that number, and that's very important. And again, that's another thing. Like I have been reading so many. As an external examiner, I get a lot of PhD thesis coming to me from different Indian institutions as well. And I've done that while I was abroad as an external examiner, and now I'm doing it as an Indian examiner. So that's one thing I see, that many times the detection limit is not even reported. Students don't even understand the concept of detection limit. So these are really very, very important concepts, especially if you want to collect good data. And good data is kind of the raw material for any good design. If we cannot have good data, our design will have problems, and we have seen that happening, especially in the solid waste field over the last 10-15 years, where we have been designing plants after plants and those plants are not working. And there are other reasons out there, but one of the major reasons for that is having bad data to start with. The data that was used to design that plant was not correct. And there is different reasons associated with that as well, which we talked about. So anything less than 0.57, what you will do with that, we'll talk about that in a minute as well, how you handle something which is below detection limit, because that's also is some sort of information out there. So but this is very, very important concept. I'll encourage you to kind of look at this part of the video again and again to make sure you understand. If you don't, feel free to ask questions through the discussion board, no problem there. Some other things that we do in terms of the QA/QC, we need to track the sample. The tracking of the sample is done using some sort of a document called chain of custody. We'll talk about that. But this other things that we talked about is more important than this. But this is also a important component where basically you need to track the sample. When the sample was collected, this is like a sample ID. When it was collected, at what time it was collected. What is any field identification number, where it got collected, what are the different parameters we want to analyze it for, and then there is a signature, kind of who collected it, what time, and then once you give it to a lab, whether it was a hand delivered, sent through a FedEx or UPS or even some sort of courier, or and then when it was received, who has received it. So there are multiple copies of it, and once you get the analysis report, you get this chain of custody copy of this chain of custody with that as well, so that you can track how the sample was collected, who has collected. So that's the reason for that, that if there is any problem with the sample, if there is any problem with the data, and you are trying to track where the problem is, how problem got into, you can talk to the people who collected the sample, get some of this personal observation which did not get reported, which did not get documented, so you can do that doing that. So this chain of custody is very, very important from a legal perspective as well. So when you go for, say something happens and it goes into a legal issue, these days in our country with so much of environmental litigation going on, NGT and other things are involved, so we have to be careful. We need to follow a good quality assurance, quality control of any projects that we are doing to do. And it's a good idea to do that even for your master's thesis and PhD thesis as much as possible, so that you establish some good practices in the lab. So let's look at some of the instruments, and then we'll talk a little bit more about this this is method detection limit part, where how to handle something which is below method detection limit. We'll talk about it. Let's look at quickly some of the different instruments which we use. So one of the instrument which you may have seen if you have been to any environmental lab is ion exchange chromatograph. Now, what is that ion exchange chromatograph? What is the chromatograph? You hear this chromatograph used a lot in like we have a IC, we have a GC, we have SPLC, we have LC. So LC is the liquid chromatograph, IC is the ion chromatograph, GC is the gas chromatograph. So you always there is a chromatograph. So what is that? What is the meaning of this chromatograph? Chromatograph essentially what it does, it say if you have a sample, you are pumping this is your column, and you are pumping the sample through, and this column has some material in there, and that material helps separate the different fractions present in the sample. So for example, if you had a sample which had some sulfide, has nitrate, nitride, bromide, fluoride, just if you're talking about anions, and sulfate, and then once the sample passes through this, since the affinity of these different anions are different to the packing material present in this particular column, things will get separated out. And based on, in a very simple way, if you think about that, you can think that this particular column, which is we put some material in which is called the packing material. So let's assume that packing material like having a lots of chairs in there. So there are lots of chairs. So once you pass through this, and all those chairs are occupied by this first we pass through what is known as eluent material, which has the highest affinity for that particular chair. So it will go and it will occupy all those positions. Now when we are passing through this sample, if the sulfate has more affinity than this particular eluent material that was said earlier, sulfate will kick out that eluent material and occupy that seat. So similar, that's how it is done, and then so it's based on that. It's those things gets occupied first, and then you pass through a substance which is higher affinity than all these anions, and then one by one these anions will be taken out. So more the affinity, that particular anion will come out later, and that concept is called retention time. That concept is called the retention time. Later, so the material first of all gets separated into different components, and then based on their affinity to the packing material and how hard they can fight with that eluent material, it's when the different times it will come out. So this was explanation more in a general way. So don't give this. Don't write like this in your exam, because I was just trying to explain you in a non-technical way. But if in the exam you have to actually write it in a technical way, where you kind of talk about, in this solid waste class will not ask you those kind of questions, but if you are doing a analytical course, environmental analysis course or something like that, where these kind of questions may be asked. But it's a one way of analyzing different anions, and we can also do cations. But with the advent of ICP now, or even AA, most of the cations are actually done using ICP or AA. And if you don't have those, many places they use spectrophotometer. A spectrophotometer is the most common instrument you see in most of the lab. Even some of these anions can be done using a spectrophotometer as well. So there are different ways of doing the same analysis. So you need to make sure you mention that clearly, which analytical instrument you used, what was the detection limit of that analytical instrument, and then you report that accordingly. So this ion exchange chromatograph, it's basically for anions. So here you can see there is as you can see over here, it has different components. So we are essentially looking at this. So there is, of course, this is an older version. This is a newer version, looks much smaller, much compact. So as you could possibly see from the computer itself, this is a older version. So there is a computer, it's a computer control. All of these are computer control these days. So there will be a computer control. Here you see the lab manual, which has all this QA/QC procedure and how to do all that standard operating procedure, and all those things are there. This part is our auto sampler. So you can prepare several samples, and this is here you can see several holes, and this part you can put all your different samples there, and those different samples can be analyzed at one go. You set up your sample, you set up your instrument, and it will be analyzing it for 5 hours, 6 hours. You can come back and watch on it from time to time. The newer version, even you can watch on it using your smartphone. So there is an app where you can look at how this machine is working, and you can even shut down the machine using that app, but you cannot restart the machine. So you have to go back to the lab to do that. But there are a lot of new things are happening. And this part is the detector part. So this is the detector part, and this is the main machine part. The top part is the detector and the bottom part is the column. So actually this top part is the detector part, and this bottom part is where we have this column. The columns are over here. The picture is not that very clear, but that's where the columns are. So what the column does, it separates different fractions, and the detector, based on different anions, have different level of conductivity. So it works on the basis of so anions have conductivity. So based on the conductivity numbers, you can predict what will be the concentration. So before you go for that unknown sample, you will again do the calibration curve, and you will know the retention time for different anions coming out. So based on that, you can do the analysis part of those. So that's kind of the basic principle of most of these machines. So ion chromatograph used for anions. You can do it for anions. Also can be done for cations as well. So that's one machine that we use quite a lot. Then other is the gas chromatograph. Gas chromatograph is an instrument to separate, again, complex gas or liquid to single component. So here injected sample are separated in gas phase, and then separated components will be detected by various types of detector. There is a flame FID, which is a flame ionized detector, or thermal conductivity detector. So based on what kind of analytes you are looking for, whether you are looking for methane, you are looking for some organic gas, or any different organic compounds, you will use different types of like a detector out there. So this is a GC is used. Then there is a GCMS. What is the difference between GC and GCMS? GCMS, in GC we are actually trying to do the analysis of the sample for which we know what we are looking for. We are looking for methane, or we are looking for benzene or toluene or xylene. So we know that we are looking for these compounds. In GCMS, if there is certain unknown in the sample, we are not even sure what kind of sample, what could be there, and that's most of the time it's true for environmental samples. So you had an environmental contamination, you would want to find out what are the different compounds present there in this this is environmental contamination. So you take your sample, you pass it through GCMS. What the GCMS has, it has it's a library. The library is present. So there are, based on the library it has had, based on its mass and charge ratio, and they will give you a so after it is equipped with a mass spectrometry, and so it has this mass spectrometry is there, which is as a detector. So it's a M/Z ratio, which is the mass by charge ratio. It is many times it's used. Once the complex chemicals are separated through the column, the separated components they pass through a high energy source in MS, and with size and pattern of fragments. So based on the library that it has, it's tried to match the compound it is trying to see with what it has in the library. So in the library we have kind of different properties of the different chemicals already given into the computer in the database of that particular instrument. So it tries to match it, and whichever closest matches, then it will say that most likely it has this contamination is benzene or toluene or xylene or TCE or PCE or those kind of matter. So then we will go back and test for that particular compound, and then using the standards of that particular compound, and just to verify whether that is present or not. So it's a little bit, it's a complex. So to maintain GCMS, to maintain ICP-MS, to maintain LC-MS or HPLC, it requires a sophistication there as well. We need some good quality hands-on trained people to run those instruments for us. It's not an easy instrument, but it's not a difficult thing to do as well. Like anything, nothing is impossible. So it can be done, but we need to have some due diligence there. So that's on GC or GCMS. Then next is SPLC. It's like other chromatograph. SPLC is also used. SPLC is usually used for more complex and greater molecular weight compounds. So usually for more complex and greater molecular weight compound can be analyzed for that. Here, unlike GC, it uses liquid as the mobile phase. And again, will not go into great detail about these different instruments. If you are interested, you can give me a call and we can talk about that, but if you in particular instrument, but I would encourage you to take an instrument analysis course, and I'm pretty sure there should be one out there. So then there is a LC, like GCMS, there is a LCMS which is used to do pharmaceutical. These days there is a lot of talk about pharmaceuticals product getting into our water bodies, so pharmaceuticals and personal care products, so LCMS is used. Some of these instruments like LCMS is pretty expensive. It's we are talking about things in crores, so it's expensive instrument, so it does require a lot of sophistication there as well. So this LCMS, then ICP, which is used to do heavy metals. Each elements can be recognized. So there is a heavy metals are done for ICP AES. These days, again, this ICP AES is a very, very old machine. This is the machine that I used for my PhD. So I'm kind of still using this picture, but the newer machine actually is even less than half of this size. But I have an emotional attachment with this picture. This was kind of the machine that I used for my PhD work at University of Florida. I have worked on this machine for nearly, after PhD, even I worked there as a research scientist. For nearly 5-6 years, this machine was my baby. So I was the person who was handling this machine day in and day out. So I have a very strong attachment to this machine. This machine is still there, and they have some newer machine there too. But it's used for heavy metals. It's used to analyze heavy metals and can be done for cations as well. And you use ICP essentially. It works on atomic emission spectroscopy. So you take it, you excite all the things that you take at a very high temperature. It works at around 5,000 to 10,000 degrees centigrade. There is a torch which is right over here in this particular box. You cannot see it from that, but it's inside box, and things get pumped in there, and the sample gets pumped, and when it gets burned at 5,000 to 10,000 degrees centigrade, it goes to an excitation state. And if you remember from that, E is equal to hc upon lambda. That will remind you of your like a modern physics from class 11, class 12, where h was the Planck's constant, c is the speed of the light, and the lambda is one for a particular wavelength. And this lambda is unique to each and every element. So for example, if you are trying to analyze for arsenic has a specific lambda, lead has a different lambda, and cobalt or cadmium has a different lambda. So based on when it gets into the excited state, if you remember from that Rutherford model of the atoms, so the electron has a tendency to come from higher elevated state to a normal state, and that's because it likes to stay in a normal state. So when it will try to come down, it will emit light, and that light that will be emitted is hc upon lambda. And when the lambda is where it's unique to each particular element, so based on the intensity of the light for that particular wavelength, we correlate that to the concentration in the sample. So such a neat, isn't it? It's such a beautiful concept. But I'm really though anyone who will come up with that idea, I don't know who, but it's a great idea. So we are based on since the wavelength is unique to each and every element, there are some interferences there. There are some interferences. Sometimes you may get some false positive, false negative numbers, and all those things will. And but when you work in the lab, you will understand that, and you will appreciate that. But again, based on, since the lambda is unique to each and every element, you can get the concentration of the sample based on the light that is coming out. So that's on ICP part, which is one of the widely used sample for heavy metals. Atomic absorption again can be used for heavy metals too. The difference between atomic absorption and ICP is atomic absorption, it's based on absorption. ICP was on emission. And graphite furnace, you can do one sample at one element at a time. ICP, you can do 25-26 elements at a time. So that's so once you have these done, then you have to work with the concentration. So once you have these analytical instruments, you have analyzed different parameters, you got these samples, you have used these analytical instruments that we talked about, you are getting the data. Now how to make sense out of the data. So in the next module, we'll try to understand how to make sense out of this data, and how to work with this data from a statistics point of view and other things. I'll give you some examples and I'll try to explain that. So again, in this particular video, what we try to do, we try to look at all the different instruments that are used and this is not the complete list. It's just some example instruments, most common instruments that we used for analysis of environmental samples, and some of the issues associated with that, or the method detection limit, and how. So I try to explain you very basics how this different instrument works, but that was. It's not an instrumental analysis course, so don't. I would encourage you to look at some instrument. If you're really interested to learn about instruments, to look at some instrument analysis book or course for that. So in the next module, we'll start looking at, once we collect data from these instruments, how to make sense out of it. So let's thank you again, and again, any question, discussion forum is there, and then I'll again see you in the next module. Thank you.